Everyone wants to know how long it takes to reach Mars. The answer isn't what you think. The countdown reaches zero, vibration, then sound. Millions of pounds of thrust push you away from Earth. The planet shrinks to a marble, then a dot, then nothing. 3 days later, the engines cut, silence. You're coasting at 39,000 kilometers per hour. The trajectory is locked, no abort option. The math sealed that decision the moment you launched. The spacecraft is functioning, life support is running, the crew is trained. Mars is exactly where the calculations say it should be. But while mission control is tracking one timeline, your body is running on a completely different one. Because the question isn't how long the trajectory takes, it's how long your biology can last while you're on it, and those two numbers don't match. Your bones don't care about orbital mechanics, your cells don't recognize fuel efficiency, your cardiovascular system doesn't know your route is mathematically optimal. They only know one thing: Earth just disappeared, and everything they need to function properly disappeared with it. The real timeline to Mars has nothing to do with distance, and it starts counting down the moment you can't see home anymore. Our solar system operates like a cosmic racetrack, and Earth is on the inside lane. We're moving faster, covering less distance per orbit. Mars is out there on the wider track, slower, more distant from the Sun. Every 780 days, just over 26 months, Earth overtakes Mars, and for a brief window, they're aligned. This is called opposition. It's the only time launching makes sense. You'd think, they're close, let's aim straight at Mars and go. But you can't, because you're not aiming at where Mars is. You're aiming at where it will be 7 months from now. You're throwing a dart at a moving target that's traveling 24 kilometers every single second. The margin for error is non-existent. Launch a day too early or too late, and your trajectory shifts. The fuel requirements change, the arrival window narrows, everything becomes exponentially more difficult. The Home and Transfer Orbit, an elliptical path calculated in 1925, connects Earth's orbit to Mars's orbit using the minimum possible energy. It's elegant, it's efficient, and it locks you into a specific timeline you cannot escape. This isn't a highway where you can accelerate or take a different exit. It's a ballistic arc determined by gravity and momentum. The spacecraft launches from Earth, accelerates into this ellipse, then coasts. For months, no thrust, just momentum and gravity. You're committed to an arc through space that cannot be shortened, cannot be adjusted significantly, and definitely cannot be reversed. Even if something goes catastrophically wrong on day 30, you're still going to Mars. The math doesn't care, which means the trajectory isn't a flight path. It's a commitment you cannot break, and it determines everything that follows. And once you accept that the trajectory cannot be changed, you realize the launch window itself is a trap you cannot avoid. The launch window opens every 26 months, not 25, not 27, exactly 26, because that's how long it takes for Earth to overtake Mars again on the inner orbit. Miss the window, and you don't wait weeks, you wait over 2 years for the next alignment. 2 years of funding, 2 years of crew training cycles, 2 years where technology ages and missions get scrapped. Some oppositions place Mars at its closest approach, 55 million kilometers. Others, because both planets follow elliptical orbits, put Mars at 100 million kilometers even during opposition. The difference isn't trivial, it's the difference between a 6-month journey and a 9-month journey. The difference between having enough life support or running out of 30 days before arrival. Between arriving with a crew that's degraded but functional, or arriving with astronauts so weakened they cannot perform the landing sequence. Mission planners calculate these windows years in advance. Planetary positions, orbital velocities, fuel efficiency, payload capacity. Millions of simulations to find the optimal trajectory. A delay of just 3 days, a minor technical issue, a weather delay, can shift your entire trajectory into a less efficient path, adding weeks to the journey. Once you commit to a launch window, you're also committing to a return window, and that return window is 26 months after you arrive. A round trip to Mars isn't a visit, it's a minimum 2.5-year mission, more realistically closer to 3 years. 3 years away from Earth, 3 years of cumulative exposure to everything that breaks the human body down. The orbital mechanics don't negotiate, they set the schedule, and the schedule creates the exposure timeline you cannot escape, which means the window isn't just a constraint, it's the mechanism that determines how much damage you'll accumulate. But orbital mechanics are just the schedule. The real constraint is the propulsion system itself, and it creates a problem that multiplies everything else. Chemical rockets work by burning fuel in a controlled explosion. The gases shoot out the back at incredible speed, pushing the spacecraft forward. It's reliable, it's proven, and it's fundamentally limited. To go faster, you need more fuel, but more fuel makes the spacecraft heavier. A heavier spacecraft needs even more fuel to accelerate. This is the tyranny of the rocket's equation, and it creates a vicious cycle that cannot be broken with chemistry alone. The Saturn V rocket that sent humans to the moon weighed 2,800 tons at launch. The actual payload that reached lunar orbit? About 45 tons. That's 98% of the rocket just to move 2% of it somewhere useful. The rest was fuel, tanks, engines, and structure that got discarded along the way. For Mars, the numbers get worse. Mars is 140 times further than the Moon. A crewed mission requires several hundred tons. Life support systems running continuously, radiation shielding, food and water for the crew, scientific equipment, the Mars landing vehicle, and the return propulsion system, because that fuel has to make the entire journey with you, sitting unused while you travel to Mars, land, conduct your mission, and prepare to come home. Every kilogram you add multiplies the fuel requirement exponentially, and every additional ton of fuel extends the journey, which requires more life support, which adds more mass, which requires more fuel. The engineering team call this the mass fraction problem. You reach a point where adding more fuel to go faster actually makes the spacecraft so heavy that you need even more fuel just to lift the additional fuel. The curve doesn't flatten, it breaks. The loop doesn't close, it spirals, which means speed isn't limited by engineering. It's limited by the physics of mass itself, and that physics locks you into a timeline that guarantees exposure. NASA's Mariner 6 reached Mars in 128 days, the fastest journey ever recorded. But Mariner 6 weighed less than 400 kilograms and carried no life support, no crew, no return capability. For a crewed mission, the calculations lock you into 6 to 9 months minimum. There is no faster route with current propulsion. Every attempt to shorten the timeline runs into the same wall. You cannot carry enough fuel to accelerate harder without making the problem exponentially worse. And while you're trapped in that 6-month minimum, locked into a timeline the rocket's equation won't let you escape, something invisible is happening to your body that no amount of shielding can stop. Earth's magnetic field protects us from cosmic radiation. That protection extends maybe 60,000 kilometers into space. You're traveling 55 million kilometers minimum. For every hour beyond Earth's magnetosphere, your cells are being bombarded by higher energy particles, galactic cosmic rays, solar particle events that slice through spacecraft walls like they're not there. These aren't the same type of radiation you get from an X-ray machine or a flight across the country. Galactic cosmic rays are atomic nuclei traveling at nearly the speed of light. When they hit your DNA, they don't just damage it, they shatter it. They create cascading secondary particles inside your body. One particle can rip through multiple cells in a chain reaction of destruction, and there are millions of these particles passing through you every day in deep space. There's no shielding technology that can stop this without adding so much mass that the spacecraft becomes unlaunchable. Aluminium walls help with some radiation, but make others worse by creating secondary particles. Water helps, but you need more meters of it in every direction. Lead is heavy and only partially effective. The only real shield is distance from the source, and you cannot put distance between yourself and the entire universe. So the radiation accumulates in your body, DNA damage, increased cancer risk, cognitive effects, and it's dose dependent. The larger you're exposed, the worse it gets. A 6-month journey exposes astronauts to radiation equivalent to getting a full-body CT scan every 5 or 6 days for 180 days straight. Even if you survive the journey to Mars, you still have to survive the surface mission, then survive the journey home. That's potentially 2 years of radiation exposure minimum. And unlike other mission risks, radiation damage is cumulative and irreversible. You can't armor your way out of it without making the spacecraft too heavy to launch. You can't shorten the journey significantly without revolutionary propulsion we don't have. And you can't turn back once you've started because the return window is 26 months away. The mission timeline creates the exposure, and the exposure creates permanent biological damage. It's not a problem you solve, it's a cost you pay, which means the journey itself is the weapon, and time is what makes it lethal. But radiation is just attacking your cells. Microgravity is attacking your entire structural system, and it starts the moment you leave Earth's gravity well. Microgravity does something insidious to the human body. In the first week, you feel fine, maybe some space sickness, but it passes. By week 4, your bones are losing density at 1% per month. Your muscles are atrophying despite exercise. Fluid is shifting towards your head, increasing intracranial pressure, degrading your vision. By month 3, your cardiovascular system is adapting to an environment where it doesn't have to fight gravity. Your heart is literally shrinking. Your immune system is becoming compromised. Wounds heal slower, infections are more likely, and the spacecraft environment is recycling the same air, the same water, concentrating any contaminants or pathogens. Month 6, arrival at Mars. You're clinically weaker than when you started, and now you have to land on a planet and conduct physically demanding work in a hostile environment. You can't stop the biological clock. Exercise helps, but doesn't prevent degradation. Medication helps, but doesn't reverse the damage. And if something goes wrong medically during the journey, there's no hospital, no emergency room, no medevac. You're 100 million kilometers from the nearest surgeon, traveling in a tin can where every system has to work perfectly because there's no backup plan the laws of physics will allow. Which means your body isn't just deteriorating, it's becoming incompatible with survival, and the timeline guarantees it. And while your body is falling apart in measurable, physical ways, something harder to quantify is happening to your mind. 6 months in a confined space with the same 3 to 6 people. No privacy, no fresh air, no horizon. Nothing but the hum of life support systems and the knowledge that Earth is a tiny blue dot in the rear camera, getting smaller every day. Communication delay grows as you travel. By the time you're halfway to Mars, there's a 12-minute delay each way. You can't have a conversation with anyone back home. You can't get real-time support from mission control. If there's an emergency, Earth will know about it 12 minutes after you do, and their response will take another 12 minutes to reach you. Studies of isolated Antarctic research stations, submarines, long-duration space missions on the ISS, they all show the same pattern. After about 90 days, psychological stress begins to manifest. Irritability, depression, interpersonal conflicts, sleep disorders. And those are in environments where you can still see Earth, where you know you can be evacuated if absolutely necessary, where the mission can be aborted. On the Mars trajectory, none of those safety valves exist. You're committed. The isolation is total, and it's not getting better. It's compounding every single day for at least 180 days. Even if every system works perfectly, even if the radiation doesn't kill you, even if your body holds together, your mind is being subjected to a stress test unlike anything in human history, which means psychological failure isn't a risk factor. It's a statistical inevitability the timeline creates. And the timeline doesn't end when you arrive, it gets worse, because now you have to come back. Let's say you make it, you survive the journey, land on Mars, and conduct your mission. Now you have to come home. The return window doesn't open immediately. Because of orbital mechanics, you have to wait for Earth and Mars to realign. That's another 18 to 20 months on Mars. Your body has now been in reduced gravity for nearly 2 years. The radiation exposure has continued, the psychological isolation has extended, and every system that degraded on the way there has kept degrading. Then, when the window finally opens, you face another 6 to 9 month journey back. Except now you're launching from a planet with 38% of Earth's gravity, with fuel that's been sitting in Martian conditions for nearly 2 years, in a spacecraft that's been exposed to Martian dust, temperature extremes, and radiation the entire time. Your bones are brittle, your muscles are atrophied beyond anything we've seen in ISS astronauts who stayed in microgravity for a year. Your cardiovascular system has spent so long in reduced gravity that it may not remember how to function when you hit Earth's atmosphere. The math is unforgiving. If you survive re-entry, if you survive the landing, you're facing months or years of rehabilitation. Some of the damage, the radiation exposure, the bone loss, the vision problems, it's permanent. Your body will never fully recover. The mission doesn't end when you get home. The consequences are written into your cells forever, which means the return isn't a homecoming. It's just a different location for the same irreversible damage. And this entire calculation assumes nothing goes wrong. No system failures, no medical emergencies, no psychological breakdowns, no unexpected solar events, no equipment malfunctions that compound into mission-critical failures. But space missions never go perfectly. The timeline just determines how catastrophic the failures become. So how long does it really take to reach Mars? With current technology, the answer is 6 to 9 months. But that number only tells you about the trajectory. It doesn't tell you about the radiation accumulating in your cells, the bone density is bleeding away in microgravity, the psychological pressure building with every passing week in isolation, the growing communication delay that severs you from any meaningful support, the orbital mechanics that lock you into a timeline you cannot escape. The problem was never the distance, it was what distance does to biology, psychology, and time itself. It's what happens when you commit human beings to a journey that doesn't forgive mistakes, doesn't allow for retreat, and compounds every small problem into something exponentially worse. We can calculate the trajectory, we can build the spacecraft, we can even solve the technical challenges of landing and returning. But the moment you leave Earth's orbit, you're not just traveling to another planet, you're entering a state where every system, mechanical and biological begins degrading on a clock that cannot be stopped. And that degradation doesn't end when you arrive. It continues through the service mission, through the wait for the return window, through the journey home. The real question isn't how long it takes to reach Mars, it's whether we can build humans who could survive what that timeline demands. Because right now, we can send the spacecraft. We just can't promise it will bring back the same people who left.